Part 3. This section is about using the correlative function, the correlation function, wherein we will do so-called autocorrelation. That means we will take the function and we will take the data and correlate it with itself as a function of lag. So that is like as a function of the separation of the two series. If you're not very familiar with autocorrelation, I'm not going to explain it here in much detail, but you should feel free to just go ahead on Wikipedia or some places on YouTube and find someone who can explain that in some more detail. So glossing over that, we are going to be applying it to the Poisson generated data that we obtained in the first part of the exercises and actually in part 2 as well. So first we'll apply to data with a constant firing rate of 100 Hertz, and the second one is also 100 Hertz but with a refractory period. So this is from part 1 and part 2 respectively. And a third one is a much more well, it's just like a slightly different way to generate data, and it's generated in a harmonic fashion. So it's a cosine function. So we have these 3 time series types of data with spikes, and we want to apply the autocorrelation function and plot the histograms of the results. Now in the lab, in real sort of neuroscientific application, this is actually used relatively commonly. For instance, when you're doing spike sorting. So when you obtain data from an electrophysiological experiment, it's worth doing the autocorrelation to create the autocolorograms of the data to see what the spikes look like and to what extent they correlate, sort of like to what extent is the spike train correlated with itself, and if there are any sort of surprising peaks, and that can tell you a little bit about the nature of the units that you're trying to spike sort. So as I said, we consider the first 3 cases. So we take the original spike data, and then we take the spike data with the refractory period. And then lastly, I just created here like a super quick generator, the Poisson generator with the particular function that they are interested in. And I just plotted the spikes here. So the thing that actually varies over time in a sinusoidal way or in a cosine way is the firing rate. So it goes up and then it goes down, but that doesn't necessarily mean that the spikes only appear here and they never appear here. It's more of a probabilistic thing. So there's much higher likelihood that the spikes will appear when the firing rate increases, and a much lower likelihood that spikes appear when the firing rate decreases. And the frequency here that we are provided with here, these 25 milliseconds, that's the period. So we should actually expect firing rate to vary, to sort of like peak every 25 milliseconds. And I just plotted that here very quickly. So just to visually check that this is actually what we get, because that is what we expect. So there is the firing rate is going up, and it's going down, and it's going up, and then it's going down, then it's going up, and then it's going down, and then it's going up, and so on. So this is actually, it's not an exact match, but it's not supposed to be. So it works for the most part. Like you can see that there are sort of like these periods of inactivity separated by periods of slightly high activity. So you can just convince yourselves that we did this correctly, and move on to the actual autocorrelation. Okay, So what we're going to do now is we're going to get the actual autocorrelation function. So correlation is basically just like an average product of a function. So we're going to use the NumPy module from Python to do this. It's just the correlate function. It's pretty similar to what you would find in MATLAB. Just make sure this mode is set to full. And then this is a bit of an extra step, but it should ideally be normalized by the length of the signal. That is, as far as I understand, the standard in the field when you're doing this autocorrelation on your own. So we do that for all three. So this is the constant rate with no refractory period, quick refractory period, and the harmonically generated spike train. And then what we're going to do is I'm not going to plot the entire thing, because what it would end up looking like is it would end up looking like essentially like a flat line with a massive peak in the middle at 0, and I don't want that. Because I don't think that's very informative. I mean, I did that in the background just to, again, convince myself that I did that correctly, but it's not actually necessary it's not the right scale to get the point that I think the book is trying to get at. So what we're really trying to get at is to understand how these three will differ. I misspelled autocorrelation. Anyway, how these three will differ in the autocorrelogram as a result of the way that these spike trains were generated. So I only plot 300 points here, and it's going to look like this. So I remove, again, this peak at the beginning, wherein this would be 0 lag, and the constant firing rate has no discernible pattern to it. So it's pretty much the same value everywhere, and it doesn't differ as a function of the lag of the separation. However, if we consider the refractory period, the autocorrelation is much lower right after 0. And that is because the likelihood of spikes appearing right after one another is extremely low, which is given the fact that we introduced the refractory period. And that's why we get this kind of like drop off here. So if I were to plot all of the values here, there would be like a big, a massive spike here. And then it would sort of drop off like this. And then lastly, and this is really beautiful, if you take the product of two sinusoidal functions as a result of the difference in their phase, but otherwise being identical, what you would end up getting is that at low values, you would get very low values when they're mismatched, and you would get high values when they are perfectly overlapping. And so this is what we get. Again, obviously the highest value in the autocorrelation, the highest average product, is present when there's no lag. However, if we just shift them around by one period, so you can think of it like you just take the sine function and then you shift it by the length of by the wavelength, and then you take the product of that. Once again, you would end up with the same product value. So that means it will be the same sort of everywhere, every single wavelength, and it will be the lowest halfway through the wavelength. And it actually ends up being almost exactly maximal at 25 milliseconds. And if you remember, this is what we were given in the exercise. This is the period which they actually provided us with. And so we have sort of like empirically verified that Again, we did this correctly because we can see this kind of periodic maximal, periodic sort of valleys and peaks in the autocorrelogram. So that's it. That's part 3 done.